Hi everyone, let's talk about how to do a hypothesis test for one population proportion. In a hypothesis test for one proportion, we are testing the hypothesis that the population proportion is equal to some benchmark value that we'll call P0. Remember, as long as n times the population proportion and n times 1 minus the population proportion, so the complement, are both at least 10, it's generally safe to assume that the sample proportion, which is the set of all the possible sample proportions of a fixed size, that sample proportion p hat is normally distributed. And so in this case, then we're going to take our critical values from the z distribution, or the normal curve distribution. So let's walk through the procedure. Okay, so our first step will be to determine the significance level, or the alpha. Remember, this is going to be 1 minus your confidence level converted to a decimal. We also want to check that our assumptions are satisfied. So in order to be sure that the set of all the sample proportions is normally distributed, then we would need to check np and n times 1 minus p using the population proportion. But of course we do not know the population proportion, so when we do this test we are going to use the benchmark proportion, the P0, instead in order to check our assumptions. Then we need to determine our null and alternative hypotheses, and you'll see as we do these are just basically the same sort of thing that we have done for all of our other hypothesis tests. For example, the test of means, the test against one population mean. So the two-tailed test is our most common situation. So in this case, as before, we are going to put half our alpha in each tail. So here's our rejection region. Alpha over 2 on that side, and then alpha 2 over here. Okay. Then for a left-tailed test, less common, and a right-tailed test, all of the alpha goes into one tail. So we might put all of our alpha in the left tail, in which case that means that our our alternative hypothesis is that p is less than some benchmark. And in a right-tailed test, all our alpha is going to be in the right tail. Okay, so let's talk about the hypotheses. Remember that P is our population proportion, which we do not have the ability to access. So all we have is the sample proportion, and so we're going to be using that in order to make inferences about the population proportion. This P0 is our benchmark value that we're going to be comparing against. So that's going to be the number we're going to compare against. And so when you actually work a problem, that P0 is going to be a number. Okay, so in our one-tailed test, the basic assumption is that the other direction, the direction not represented in our alternative hypothesis, is either impossible or of zero interest. And generally it's the impossible situation. If it's of zero interest, you have to have a really good rationale for doing that, because choosing a one-tailed versus a two-tailed affects the critical values, and therefore it affects whether you will end up getting what we call a statistically significant test, where we reject the null hypothesis. So null hypothesis H0, remember this has always got an equal sign, and then the other one is some sort of an inequality, either a general two-sided inequality, not equal, or a direction. Once we have that, we use our alpha level and our hypotheses to sketch the region. Once we have sketched our region and determined our alpha level and our hypotheses, then we're going to use the normal curve table to figure out the critical value. Okay, and that critical value is going to be where our color changes from shaded to unshaded. It is also possible to use the p-value approach on these hypothesis tests, in which you use technology to determine the p-value, which is the probability
that if H0 is true, that you get a result at least as extreme as the result in your sample.
But in this video, I'm going to talk about the critical value approach. Then we're going to use our test statistic. So as always, in our test statistic, we're going to follow the same general pattern. Our test statistic will always look like this. We're going to subtract what we're comparing. And so in that case, that means the sample proportion p hat and the benchmark p0. And then we are going to divide by the standard error. So from that, you can really see what the standard error is going to be in our hypothesis test. And you saw something similar to that when we did the confidence intervals for one proportion. Okay, so that square root there, p0 times the complement divided by n with the square root, that's going to be our standard error. Then we put the value of our test statistic on our picture and decide whether it's in the rejection region or not, and that tells us whether we reject the null hypothesis or we do not reject it. Let's do an example. Okay, suppose we have a local police department that claims that over 70% of false alarms from home security systems are from human error. A researcher analyzes a random sample of 450 police files for false alarm calls. Out of the alarms in the sample, 324 were caused by human error. And so then we want to ask whether this sample provides evidence to support the police department's claim. And we are asked to use a 95% confidence level. Okay, so let's lay out our information here. First, let's write down the sample information. And I like to divide my work on the hypothesis test into 6 squares, just to keep me organized and on track. So for the sample information, my sample size is 450, and if you hear a cat in the background, that is just a very loud cat who doesn't like to not be the center of attention. I guess she has something to say. So she's now on a video. Okay, so my sample size is n equals 450, and then our sample proportion that's going to be our p hat. So remember, for this we take x over the characteristic, x meaning the number with the characteristic of interest, and we divide that by the sample size. So for us, what's our characteristic of interest? The false alarm is caused by human error. And you may want to write this down so that it's well defined and clear. Okay, and so that's going to be what? 324 divided by 450. Okay, and so this turns out to be about 0.72. And the reason I rounded to 2 decimal places is because if you look ahead a little bit to our benchmark, it says 70%, so that's basically going to end up giving us 2 decimal places as well. Okay, let's check to see if our assumptions are met. So what we need is basically, if we make a table that summarizes the entries that have the characteristic and the entries that don't. We want all the cells in our table to be at least 10. So you can make yourself a little table like this. And even if you don't make out the table, even if you don't create the table, you can conceptually do the same thing. So there are 324 that were caused by human error, right? And so how many are not caused by human error? 450 minus the 324 gives us what? 126. Okay, and so both of these are larger than 10, so that is what we want. Okay, now let's look at our hypotheses. Okay, so my P is going to be the proportion of false alarms caused by human error. So if you want, for space, you can write that over here instead. You don't have to keep everything in the same box as I did. Usually that works okay, but sometimes the spacing doesn't work out perfectly. Okay, so now let's write down our H0 and our alternative hypothesis, which you can indicate either with HA or H1, either is fine. Okay, so what is our benchmark? Let's go back and look at our problem. So what are we comparing against? We're comparing against the 70%, right? So what our claim is going to be, our H0 is going to be that P is equal to 0.70. Now that's not the claim of the police department, but that's the claim represented by the H0. Okay, in other words, that's a statement that's being tested. Remember, you're always going to have an equal sign for this one. And then for the alternative hypothesis, we're also going to have P. We need to now decide whether it's one-tailed or two-tailed. So we go back and we look at the problem and we see if they are steering us in a direction or if they're just leaving it to where there's no reason to go one direction, bigger or smaller. So here, what you want to look at is this, over 70%. So this over right here, this over is telling us that we have a one-tailed test. So basically the P over 0.7 is going to be our alternative hypothesis. Okay, now we also want to write down our alpha. So our alpha is what? 1 minus the 95%, except we write it as a decimal, so this is going to be 0.05. So that's our alpha. And while we're at it, let's go ahead and look and be careful about our benchmark here. So my benchmark is, I'm going to call it P0 equals 0.70. Okay, so then the complement, or basically the probability of the complement, I should say, gives us, so that's going to be 1 minus our benchmark. If you want, you could call it Q0. This is going to be 0.3, right? Okay. So now let's sketch our picture. Okay, so here's our picture, and then because it's a one-tailed test, which direction is our shaded area going to be? It's a one-tailed test, so it's going to only be in one tail, and it's going to be to the right because we have greater than 0.7. So we're going to put this over here. and this is going to be all the alpha. So this is going to be the whole 0.05 is going to go over there. Okay, and then where the color changes, this is going to be our critical value. So I would call this Z 0.05. As always, that subscript represents the area that's to the right in that tail. Okay, we don't know what that is yet, but we're about to. Okay, so now we need to find our critical value. To find the critical value, let's think about the fact that the right tail area is 0.05. So my right tail area is 0.05. And so that tells me that the area to the left of my critical value is what? 0.95, because the area under the curve has to be 1 altogether. So what we're going to do is we're going to look up area equals 0.95 in our normal curve table. So let's go to our Z table. So I'm going to come over here to my Z table, and to get an area of 0.95, I want to go to the positive half of the Z table. So I come down and I want to get the area that's as close to 0.95 as possible. So let's see, how close can we get? Ooh, 0.9495, that's close. 0.9505 is also close. In fact, it looks like it's halfway in between. I think we've seen this before, haven't we, if you've watched the previous videos. So we're going to split the difference since it seems to be halfway in between. If it was much closer to one than the other, then I would pick the closest one. So that's 1.6 for the integer place and the tenths place, and then we're going to come and get the hundredths place from up here. So we've got these two, so it's going to be halfway in between 1.64 and 1.65. So that's what we're going to go with. .64 and 1.65, and so you could average those two, or you could mentally figure out what's halfway in between. That's going to be easier if you put a 0 on here, because what's halfway in between 640 and 650? 645, right? And so then that tells me that my critical value is going to be Z 0.05 is equal to 1.645. And that's it. This one comes up really, really often, so it might be a good idea to memorize the values for Z 0.05 and Z 0.025 and maybe Z 0.1 so that you'll have them handy or have them written down in a separate area. But that's how we get it from the table. So now what we need to do, actually we need to do our test statistic, but before we do that, let's go ahead and put this 1.645 on my picture. So I'm going to scroll back up. Here is my 1.645. We only have it on one side. So when we get our test statistic, we'll compare to that to see if we reject H0. Okay, so now we need to calculate our test statistic. Okay, so for the first thing that we want to do is find our standard error. So when we do our standard error, we want to use the benchmark value for our P0, or our location of P in our standard error. So sigma of all the p hats, that's our standard error, is going to be, now this is going to be approximation because we don't know the population proportion. So here's our formula. P0 times 1 minus P0 divided by n, take the square root of the whole thing. Okay, so this is going to give me the square root of, okay, what's my P0? That's our benchmark that we're testing in our H0. Okay, and so that's why if you look here, I did the complement here, so I've already figured out what 1 minus P0 is, so I don't have to do parentheses in my calculation. So I want 0.7 and I want 0.3. And then we divide by our n, which is 450. And then this should give me about 0.0216025, and I always write a lot of decimals for these, more than I would for the mean, because keeping in mind that proportions are always going to be smaller than 1. So to keep from losing important information, you need to extend them out further. I will store this in my calculator in a variable, like for example variable a, so that I can retrieve it later without rounding. Okay, so once I do that, then we do our test statistic. Okay, so for this, p hat minus p0 divided by that standard error. Okay, so remember our general principle. What are we going to do when calculating our test statistic? We're always going to subtract what we're comparing. And then we're going to divide by the standard error. And I always calculate the standard error separately because for some of these, and that's going to be true even more so in the future sections that we do, the standard error is a little bit complicated, so it's better just to do it first and separately and then stick it in the denominator. Okay, so here this is going to give me, what's my p hat? 0.72 minus 0.70, and then I divide by this number, but I'm not going to retype it. I'm going to use the stored value that I retrieve in my calculator. So if I stored it in A, I'll tell my calculator to go and do value A. And so this turns out to be about 0.926. So I'm going to go back up here and put that on my table. Sorry, put that on my picture. So where is 0.926 going to be? 0.926 is going to be over here somewhere, right? So you see that is not in our rejection region because it's smaller than the critical value. Should say closer to the mean than the critical value. Okay, so now let's write our conclusion. Okay, so we are not in the rejection region, so we are going to not reject H0. And then we want to also write it out in words. So basically what this tells us is that this particular sample does not provide evidence and since we had a claim from the police department here, let's go back and see if we can't reread that. So what is our claim by the police department? That over 70% of the false alarms are caused by human error. So look, that's my alternative hypothesis, right? So since we did not reject H0, that means we do not have any evidence in favor of the alternative hypothesis. So we always use the null hypothesis as starting default assumption. And so if we don't reject it, then we're going to still stick to it. So we do not have evidence that it's higher. So this sample does not give us evidence that the rate of human error in false alarms is over 70%. Okay, so you always want to be able to reframe your conclusion in terms of actually what's going on in the problem. Okay, I hope this example helped you. I will see you for the next one.